Okay, now that we define the setting and the model, it's time to define what is a matching algorithm and then what is the objective of the planner in order to close the framework. So let's start with matching algorithm. It's quite simple. So the planner at each point in time observes the set of agents in the market, the nodes of the graph. The planner observes the set of compatible pairs who can be matched to whom, or the links of the graph. I'm going to call this G of t, the graph at time t. The planner also observes which agent is critical, and because this is a continuous time model, the probability of having two critical agents at the same time is just zero, so at most I will have one critical agent at each point in time, and as I promised to you, I'm going to relax this assumption later from both directions, but for now let's stick to this. And then a dynamic matching algorithm is simply a function from this network and the information about which node is critical to a matching. And a matching is a set of disjoint links, a bunch of links that do not have any nodes in common. It could be potentially empty. In order to make sure we are in the same page, let me just show you one example. So the planner observes the set of agents in the market, as you can see here. The planner observes links, and the planner observes that this agent here is actually critical, and then as a function of this information, the network and the set of critical agents, the planner should pick a set of disjoint edges. For example, this one, the planner decides to match these two together and does that two together, and when I match these, four agents together, they leave the market, and all links connected to them will actually disappear from the graph, and this is how the system evolves. By the way, this is not necessarily a good or a bad matching algorithm. This is just one example of a dynamic matching algorithm. In order to see what is a good or a bad matching algorithm, we have to actually define the objective, and that's exactly what I'm going to do now. What is the objective of the planner? For now, let's actually stick on the following assumption. Suppose waiting cost is zero. So suppose agents don't care about when they get matched. We are going to relax this later, either in these talks or in the paper you can find it. But for now, I'm going to assume that the cost of dialysis is much less than the cost of dying, for example. That's not, by the way, necessarily true in kidney exchange, so this is a simplifying assumption, and I will tell you why I impose this assumption. In some sense, we are going to upper bound the value of waiting. So if waiting cost is zero, then you get the maximum possible thing you can get from the value of waiting. I will get back to this point later. But let's continue with this assumption. So the per period waiting cost is zero, and the only waiting cost is that agents may die, may perish. In this world, the goal of the planner is simply to minimize the fraction of agents who perish. The fraction of agents who become critical, we cannot match them, they leave the market unmatched. I can make it a little bit more formal, it's just the same thing. So run the system from time t, time zero to some time cap t, a large time. I just start simulating this model that I described for you, and then I choose a matching algorithm according to some rule I decide to match agents. And then I calculate the following fraction. I calculate the expected number of agents who are going to die under this matching algorithm, and I divide it by this normalization factor, which is simply the expected number of agents who arrive to my market in t periods. Why? Because at each period, m new agents come to market in expectation. I have t periods, mt is the expected number of agents who arrive by time t, and I'm going to call this fraction the loss of a matching algorithm. So the loss of a matching algorithm basically tell me the fraction of agents, the expected fraction of agents who come to the market, do not get matched, leave the market unmatched. Now, what I've been telling you so far is a well-defined Markov decision problem. I have a Markov decision problem in which I know exactly what is the stochastic model, the arrival rate, link formation, and departures. I know what is a matching algorithm, and I know what is the objective function of the planner. In principle, I should be able to solve for the optimal matching algorithm. If you have a supercomputer, in principle, you can solve it. The problem here is that why we cannot solve this problem. The issue is that each state of this Markov decision problem is a network. So I have to make a decision for each network plus this information about critical agents. And if you don't know, it's actually very good to know that the number of networks that I can build on n nodes is of the order of 2 to power n squared. So if you have only 30 nodes, so if you have only 30 patient donor pairs, the number of states that you can have, and for each one of those states you have to make a decision, is more than the number of atoms in the observable universe. So this problem is computationally complex. And that's exactly why I'm going to design some algorithmic techniques in order to be able to solve this problem. And we are going to do this in the next video.